Marhaba. Okay, this will be our last session on the chapter of functions. Okay, I just want to define what is the graph of a function. It will be a set. Okay, so given a function f from a to b, the graph of f is the following set. Okay, we will denote it by graph of f. And what is this set? This is the set of all pairs a comma b. So remember, this is an ordered pair. It's a 2-tuple such that the first element of the pair a belongs to the domain of the function, and the second element of the pair is the image of a, and f of a is the second element b. Okay, so this is the definition of the graph of a function. So it's the set of pairs whose first element is an element of the domain of the function, and second element is the image of the first element. Okay, so let me say remark that when we have functions whose domain is the set of real numbers and codomain is the set of real numbers, then the graph of f will be a set of points in the Cartesian plane, right? So for example, we can sketch it. In this case, the graph, for example, all the points here will be the graph of f, say, where f is the square function. This is the parabola, but so there are two ways to look at graphs. Either when the domain is R and codomain is R, then we can sketch it as the set of points. This will be the curve passing through all these points. But in general, this is the definition of the graph of a function. It is the set of all pairs whose first element is an element of the domain of the function, and second element b is the image of a, where a is the first element. Okay, so let's take an example. Okay, let's have this example of a function f from the set of integers to the set of integers, which is the square function, where f of n is n squared. Okay, then what is the graph of f? Give me some. Let's have some examples of elements in this set. Okay, let's write the definition of the graph first. This is, say, the set of all integers mn such that m is in the domain, which is z, and n, the second one, is the image of the first one. So it's f of m, right? But f of m is m squared, so n is m squared. So this is the set of all pairs m where n is m squared, such that m is in z. So let's list some elements here. We have, for if m is 0, 0 squared is 0. This is one element, 1, 1. Okay, 4, 16. Negative 3, 9. And so on. So this is the graph of this function. Again, the graph of a function is the set of pairs where the first element is in the domain and second element is the image of the first element under the function f. Okay. Now what we want to do before finishing this section, we want to introduce two important functions. The first one is called the ceiling function. Okay, so let me say, or first the floor function. The floor function. So I want to give you two examples of functions, the floor function and the ceiling function. Let's start with the floor function. What is the floor function? It's denoted by this symbol, and it's a function whose domain is R and codomain is the integers, and where if you choose a real number in the domain X, then its floor, the image of this real number, is the maximum integer less than or equal to X. So the maximum K, but K belongs to the integers, such that K is less than or equal to X. So how to picture this ceiling function? Imagine we have the real numbers but written vertically. So this is, say, 10, 9, 11, and so on. So if this is X, say X is 4.6, okay, X is a real number, then the floor of X is all integers K less than X. So what are the integers less than X? You have 0 is less than 4.6, 1 is less than 4.6, 2 is 3, and 4, but then 5 is bigger than 4.6. So which one among all the integers less than 4.6 is the largest? It is 4. So we say that this floor of 4.6 is 4, because 4 is the greatest integer less than or equal to 4.6. Now what's the floor of 7? It is 7, because 7 is the greatest integer less than or equal to 7. Okay, what is the floor of negative 2.3? Okay, let's draw the number line vertically. So here is 0, say, here is negative 2.3, and I want to look at all integers below negative 2.3. For example, here is negative 4, here is negative 3. Where is negative 2? Negative 2 is here, right? It's above negative 2.3. So what is the largest integer below this number? It is negative 3. So the floor of negative 2.3 is negative 3. Now similarly, we define the ceiling function. What is the ceiling function? It is denoted by this symbol, and it's again a function whose domain is the set of real numbers and the codomain is the integers. So it takes as an input a real number and produces as an output an integer, and the ceiling of X is defined to be the minimum integer, the minimum among all the integers which are greater than X, so such that K is bigger than or equal to X. Okay, so let's see what is the picture here. So if this is X, say, we look at all the integers above X and we choose the least one. So this one will be the ceiling. Okay, let's have an example. For example, what is the ceiling of 3.1? Okay, so imagine, put 3.1 on the number line. Look at all integers above 3.1. So we know, say, 7 is above, 5 is above 3.1, 4 is above 3.1. Okay, 3 is below 3.1. So the minimum integer above or greater than or equal to 3.1 is 4. Okay, now what's the ceiling of 3? It is 3. The ceiling of any integer is the integer itself. What's the ceiling of negative 2.4? So again, where okay, say this is negative 2.4. I want to look at all integers greater than or equal to negative 2.4. So where is negative? Say this is 0, this is negative 1, this is negative 2, but here is negative 3. So the least integer greater than or equal to negative 2.4 is negative 2. Okay, so this is negative 2. So this is the ceiling function and this is the floor function. So let me say it in words. The floor of x is the greatest integer less than or equal to x. Okay, so you see x, you look at all the integers, whole numbers below x, and you choose the greatest one. This is the floor. Now the ceiling of a real number x is what? Is you look at all the integers, all the whole numbers bigger than x, and you choose the least one. And this will be the ceiling. Okay, let us prove some property about the floor function. Let's call it a lemma. Okay, what is this lemma? The lemma says let x be any real number and n be any integer. We want to prove an if and only if statement, so a biconditional statement which says that the floor of x is this natural number n, integer n, if and only if x is sandwiched between n and its successor. But the equality x is bigger than or equal to n and strictly less than n plus 1. We want to prove this. So since this is a biconditional statement, we need to prove both directions. So suppose here we want to show if the floor of x is n, then x should be between n and n plus 1, where equality holds for the left hand side. Okay, so suppose the floor of x is n. Okay, what does it mean that the floor of x is n? Then n is the greatest integer, so n, by definition of the floor, n is the greatest integer less than or equal to x, right? So, in particular, n is less than or equal to x. It's not only less than or equal to x, it's the greatest one. So we proved this inequality. Now let's prove. Now it remains to show. We will show that x is strictly less than n plus 1. We will show this by contradiction. So for the sake of contradiction, assume the contrary. Contradiction. Assume that it's not the case. So assume that x is bigger than or equal to n plus 1. Now, if x is bigger than or equal to n plus 1, what can you tell me about the floor of x? This means that the floor of x is what? Is the greatest integer below or equal to x. But since n plus 1 is below or equal to x, then the floor of x is bigger than n plus 1 or equal. And n plus 1 is strictly bigger than n. So this means that the floor of x is not equal to n, which is a contradiction, because our assumption is that the floor of x is n. Okay, so this can't happen. This can't happen. Our assumption cannot happen. And this means that x must be strictly less than n plus 1. So we proved x is strictly less than n plus 1, and we proved that x is bigger than or equal to n. So therefore we proved that x is bigger than or equal to n and strictly less than n plus 1. Okay, this is what we showed. Now this is the forward direction. For the reverse direction, we want to show that if x is bigger than or equal to n and strictly less than n plus 1, then this implies that the floor of x is n. But let me say this in words. Look at this inequality. What does it mean? Maybe I should use a figure here. So this is x, and this is n, and this is n plus 1. Okay, so x is bigger than or equal to n and strictly less than n plus 1. Now what is the floor of x? The floor of x is the greatest integer below or equal to x. So look at the integers below or equal to x. Now one of them is n. But there is no greater integer than n which is still below or equal to x, because the successor of n is already above x. So this means that once we have this, it means that n is the largest integer below or equal to x, which means that n is the floor of x. Okay. So this shows the opposite direction. So let me write the lemma we proved again. So it says that if x is a real number and it is between n and the successor, then this is true if and only if the floor of x is n is also true. So these two statements are equivalent. Either both are true or both are false. Okay, now we want to use this lemma to prove another property. So let's prove another lemma. Let me call this lemma star. Okay, we want to prove that the floor of x, again, let x be a real number and n an integer. We want to prove that the floor of x plus n is equal to the floor of x plus n. Okay, we want to prove this, so show this. Then this holds. Okay. Again, what does this say? We have a real number x. If we add an integer to it, n, we get another real number x plus 1, n. If you take the floor of this number, this will be equal to the floor of x plus n. Okay, so we want to prove this, and we want to use the star, this lemma. Okay, how we will do this? So let the floor of x, what is the floor of x? It is the greatest integer less than or equal to x. Let's call it m. Okay, now, okay, the floor of x is equal to m if and only if by star, by what we did here, x is between m and the successor of m. But this is now, we will add n to all sides, so if and only if m plus n is less than or equal to x plus n, strictly less than m plus n plus 1. Look, what does this say? This says that x plus n is sandwiched between the integer m plus n and its successor. So again, if we use the star lemma again in the opposite direction, this means that the floor of x plus n is m plus n. But what is m? M is the floor of x plus n. So this shows that the floor of x plus n is equal to the floor of x plus n. Okay. Now, before I finish this section, I want to say a few comments about functions. So we want to say a few comments about functions f, whose domain is the set of real numbers and codomain is the set of real numbers. Okay. So what is this comment? So let f be a function from R to R. Then you can imagine that we can sketch now the graph of this function, because the graph will be set of points of real numbers, and every pair of real numbers can be imagined as a point in the Cartesian plane. Okay, so consider a function whose domain is R and codomain is R as well, and we want to see what it means for this function to be injective in terms of horizontal lines intersecting the graph of the function. So let me say point 1, then f is injective. Remember, f is injective means it doesn't assign the same image to two different points in the domain. If and only if every horizontal line intersects the graph of f at most once. Okay, so here is at most. Why is this? Suppose we have a graph of a function. Why I was allowed to sketch it in this form? Because the domain is R, and the domain here is represented by the x-axis, and the codomain is also R, and it's represented by the y-axis. Suppose we have a horizontal line, say the red one, which intersects the graph more than once, so 2 times or 3 times. What does this mean? It means that there are 2 points or more, so this point and this point. So if this is A and this is B, this means that f of A is equal to f of B. The image of A is equal to the image of B, and this shows that this is not injective, right? Because there are 2 points, namely A and B, in the domain which have the same image, and this doesn't mean injectivity. Does not mean that the function is injective. So for injectivity to hold, whenever, so maybe I sketch the graph of a horizontal of an injective function. Look at the graph of this function, for example, is a straight line. Now let's look. This is a horizontal line. It intersected at most once. Here's another horizontal line. So every horizontal line intersects the function exactly once, or at most once. Okay, maybe here it doesn't intersect it at all. Okay, so this means that the function is injective because every horizontal line intersects the function at most once. Now let's move to surjectivity. This is the second point. So the function f defined from R to R is surjective if and only if every horizontal line intersects the graph, its graph, at least once. Its graph at least once. Why is this? Let's see. What does it mean for a function to be surjective? And this function is defined from R to R. It means so this axis represents the codomain. It means that every point in the domain must be at some point, must have a pre-image. So at some point we must have a pre-image for it. So this point has to be on the curve, and if you choose another point, it has to have a pre-image. So the curve of the function must look like this, for example. Okay, whenever you have a horizontal line, it must hit the curve, right? Because whenever we choose a point in the codomain, we must have a pre-image for it. Okay, this means that the function is surjective. Maybe, okay, I'll give you another example. Look, maybe it intersected more than once, right? Okay, so look, this means that this function, this point in the codomain has how many pre-images? It has 3 pre-images. This is the first, and this is the second, and this is the third. Okay, it has 3 pre-images. But at least once means that every point in the codomain has at least one pre-image, and this is the definition of surjectivity. Okay. Now, what the third point is that f from R to R is bijective if every point in the codomain has exactly one pre-image. So is bijective if and only if every horizontal line intersects the graph of f exactly once. Right? Exactly once means it is injective and it is surjective. It means also that every point in the codomain. Okay, so we can think, for example, of this function. Sorry. Look at this function, for example. And now, whenever we do a horizontal line, it intersects the graph exactly once, which means that every point in the codomain has exactly one pre-image. Every point has exactly one pre-image. So here's another horizontal line. So this point is in the codomain and it has exactly one pre-image. And this is a property of being bijective, right? That it is both injective and surjective. Okay, so to sum up this section, so it's about functions, and the functions are assignments from a set A to a set B. We studied injective functions, surjective functions, and bijective functions, which are both injective and surjective. And we introduced an operation on functions where the composition of functions. We talked about the inverse of functions, where the inverse exists when the function is bijective. And finally, we studied two special functions called the ceiling and the floor functions. And this last comment, it's a brief comment about how can we tell whether functions from the real numbers to the real numbers are injective, surjective, or both using horizontal line tests. So you keep drawing horizontal line on the curve of a function, and if every time you draw it, it intersects the graph at most once, so it means either it does not intersect it or it intersects it once, then it is injective. If every time you draw a horizontal line and it intersects the graph at least once, so every time every horizontal line hits the graph of the function, then it is surjective. If every time you draw a horizontal line, it intersects the graph of the function exactly once, then this function must be injective and surjective, which means it's bijective. So we stop here.